In this example, we have a person who is pulling a sack of gravel that is bungee corded to the wall. So we're given the pulling force, the angle of the pull, mass of the bag, spring constant of the bungee cord, static kinetic friction, and initial length of the cord. And then it asks, how do we find acceleration right when it starts moving, and then acceleration after it's moved by 0.5 meters. So we'll work this out. First, step one always is draw free body diagram. So we have the block. We've got the weight pulling down, normal force pushing up, the pulling force pulling to the side and up. We have spring force pulling to the right, and then we've got a friction force which opposes the direction of motion. So the person's trying to pull it to the left, which means the friction force goes to the right. Step two, we assign a coordinate frame. So let's say we have, if it's supposed to go to the left, then we'll say X goes left, Y goes up. And then step three is write the equations. So in the Y direction, sum of the forces in the Y equals 0 because the block is not moving off of the surface. So that equals the normal force, which goes up. Also, there's a component of the pull that's pointing up. So we'll have plus P sine theta, because the sine component pulls up, the cosine component goes to the side, and then we subtract the weight pulling down. So if we rearrange this, then we'll get N equals mg minus P sine theta. Then if we put numbers into that, this equals 22 times 9.81 minus 300 sine of 30 degrees, which equals 65.8 newtons. Now, we know that static friction and kinetic friction we both have to deal with. And friction force equals mu times normal force. So for static, we use static coefficient. So that's going to be 0.8 times 65.8, which equals 52.7 newtons. And then for kinetic, we'll have 0.4 times 65.8, which equals 26.4 newtons. And then in the x direction, this is the direction that it should accelerate. So Fx equals ma. So in the x direction, we've got P pulling to the left. So P cos theta minus friction force, and then minus spring force. Now we've got to check static friction. So let's say here we'll check static. We got to see if the block actually moves. So if the block moves, acceleration would be 0. So we have 0 on this side, and then we compare that to P cos theta minus all this stuff. Well, at the beginning, then the bungee cord has not stretched at all. So before it started moving, there's no stretch. We can get rid of this. There is no force from the spring if the spring hasn't stretched any. So here we'll just have that 300 times cosine of 30 minus the friction force, which we have to use static friction, is 52.7. And this comes out to be 207 newtons. Well, 207 is greater than 0, so the person is able to pull hard enough, and the sack moves. Now, we can anticipate that the sack moves because the second part of the problem is find the acceleration at L equals 0.5 meters. So we know it must have moved to 0.5 meters. So we could have skipped this step, but if we didn't know if it moved or not, we would need to check. So then we'll check dynamic. For this, we need to actually find value of the acceleration. Well, from this equation, we know acceleration equals P cos theta minus kinetic friction minus K times L minus L initial divided by M. So if we put numbers in here, then we have 300 cosine of 30 minus 26.4 over M, which M is 22. And then we'll subtract the spring force, which is 10, times I stretched to 0.5, initial includes 0, over that. So I split it up into two parts because it asks for acceleration at the start and then after the stretch. So this first part will be acceleration after the start, and then if we include the second part, is acceleration after the stretch. So here we'll have A equals, this is 13.3 minus 0.23, which equals 13.1 meters per second squared. So this is A after 0.5. And then this part is A initially before the stretch. So to recap what we did here, we're given all these variables and we need to find acceleration. First, we drew the free body diagram with all the forces pointing on the object. And we included friction in there and saw which way friction goes. So then we assigned a coordinate frame with X pointing in the direction of motion and Y perpendicular to it. Then we wrote the equations. Sum of the forces in the Y, sum of the forces in the X. We check static friction to see if the block moves. And then we check dynamic friction when acceleration is not 0 and determine the actual value of that acceleration. At first, the spring has not stretched anything, so acceleration will be greatest. It's at 13.3. And then as the spring starts to stretch, the acceleration decreases because the spring is pulling back against the person. So after a half meter stretch, it came out to be 13.1 meters per second squared, which is lower, so that's good.